Welcome to the online course of our second chapter, the electric field in CLIL course physics. Before we can start, we always start off with a bit of useful vocabulary for this chapter. The first one being celestial body, being hemellichaam, gravity, of course, being zwaartekracht. This one is probably not quite as well known. It's tangent line, and you can translate that as raaklijn. It's a term you know in maths. It's a line that only touches another curve in a single point. Radial is radiaal, and bipolar is, of course, bipolair. Now, why are we talking about celestial bodies at the start? Well, we're going to first discuss what force fields are in this chapter. Previously, you have already encountered a typical force field when we were talking about gravity fields in the third year. Now, just to recap, what is a gravity field? Well, it exists around planets, moons, etc. In other words, celestial bodies. Right? Now, these gravity fields, they can cause, this should have been a force, with a mass at a point, with mass as the point of engagement. Meaning, if you bring an object with a mass inside a gravity field, you will get a force. And that force is called gravity, abbreviated by Fz in Dutch. Fg in English, of course. Every different celestial body has its own strength of gravity field. We've used as an example in the third year, the gravity field on the moon is only 1.62 newtons per kilogram, whereas the gravity field on Earth is 9.81 newtons per kilogram on average. So it just depends on the celestial body you're talking about. Now, those gravity fields are more or less known for every celestial body. How were they able to determine how much gravity field there would be in, on planets such as Saturn, etc.? Well, it depends on two major factors. The first one being the distance to the center of the celestial body. In other words, the radius of the body. Now, I did a bit of research. For Earth, as an example, that is 6,371 kilometers. Now, that is the average radius of Earth itself. Now, usually when we are talking about gravity, we can consider that we're pretty much on the surface of the planet. If you compare this, for instance, to the highest point on Earth, being Mount Everest, which is an enormous mountain, being 8.8 kilometers tall, well, when you look at how much difference that makes, whether you're talking about 6,371 or 6,379 kilometers, it makes virtually no difference in this case. It is actually calculated, it isn't even a single percentage point difference. It's 0.2%. So, for gravity, you can say that the distance to the center of a celestial body is pretty much a constant. Because you cannot really escape that high up on Earth without exiting the atmosphere. The second thing that is pretty much a constant is the mass of a celestial body. Now, I didn't quite go into details and Google that one. You should be able to do so yourself. But the mass of Earth is essentially also a constant. Even if a meteorite would hit it, it's not like it would be a vast increase in the total mass of Earth as a whole. Right? This leads to an equation that you are probably not as familiar with, the universal gravity equation. And what is the universal gravity equation? Well, it calculates the amount of gravity force between two objects, one with mass 1 being your celestial body, and the second one is your own mass in this case. Now, let's just recap. What is this universal gravity equation? Well, it is a certain constant value, g, capital G in this case, multiplied by the first mass of the celestial body and divided by the distance to the center of the celestial body. Now, like I've said, that distance is a constant. The mass of the celestial body is pretty much a constant in this case, meaning all of this is a constant in this case. That constant being capital G times the mass of Earth divided by the radius of Earth to the second. That means that we can draw a similarity to any electric fields around it. Quite simple. An electric field, and feel free to pause the video and fill it in as you go along, it exists around charged objects. It can cause a force on other charged objects in this case. And what does it result in? It results in a Coulomb force, an electric force in this case. Now, also, like we said, every celestial body has its own strength of gravity field. In this case, every charged object has its own electric field around it. What determines the strength of this electric field? Well, it is determined by, so the electric field E is inversely proportional to the distance where you're measuring the electric field. And that distance is usually in a point that we call a random point P in this case. So it is inversely proportional to the distance to the charged object, the center of the charged object. What is it not inversely proportional with, but directly proportional? Well, it is directly proportional with the amount of charge of the charged object. Now, quite often we call this the source charge, or in Dutch courses, the bronlading, meaning we consider the charged object to be the source of the electric field. In general, we also know what Coulomb's law was. We know the amount of force that exists between two charges. It was Coulomb's constant K times charge 1 times charge 2, and it was divided by the distance separating the two squared in this case. Now, let's consider what is, part of the first charge. Well, it is a certain constant. It is multiplied by charge 1. However, in this context, we're not going to be talking about charge 1. We're going to be talking about the source charge of our electric field. And it is dependent on distance squared, meaning these two are enormously similar. If I want to know how strong my electric field is, it is essentially constant, Coulomb's constant K, times your source charge divided by the distance squared. Now, in this context, there is one thing that we have to take into account. This equation is not quite done yet. In order to avoid negative forces and all of that nonsense, we always worked with the net values of each charge. Right? So even if one was positive and the other was negative, we never took that into account to calculate the amount of force. What did we take into account, however, was the sense of the vector of the force. It could be when they are attracting towards each other or when they are repelling away from each other. Well, we'll be doing something similar with the electric field. We are also going to calculate the strength of that field vector by taking the net value of your source charge. So we don't take into account if it's positive or negative, and we divide it by distance squared. This is the next point I want to make. This electric field, even though we have just made the equation for the magnitude of this vector, is still a vector, meaning it has a point of engagement. Now, G is also a vector, gravity, and I make the similarities, or I point out the similarities in my course between the two. What is the point of engagement of a gravity vector? Well, it's usually a point on the surface of a celestial body, right, where you want to determine the gravity field. The orientation of G is also always very easy. It's always vertical, and because we're always talking about an attraction when it comes to a gravity field, never a repulsion, the sense of vector G is always towards the celestial body, towards the surface of Earth, as you've seen in your third year. And the magnitude of G was pretty much a constant number. Why was this a constant number? Why, when you look at G in its grand total, this is a constant, this is a constant, this is a constant. In other words, that's just a constant as a whole. Now, for electric fields, it's not quite as simple. You've got a point of engagement, which is a random point P near a charge that you want, right? The vector also has an orientation, and this is pretty simple. It's always a straight line between your source charge and the point P where you want to know E. However, an electric field can be both causing repulsion or attraction. So we have to make that distinction. And we make that distinction with the sense of the vector of E. Meaning, a positive charge means the sense is away from the charge, and a negative charge means the sense is towards our charge Q. And the magnitude of E, finally, well, can simply be calculated depending on the source charge in Coulomb and the distance in meters. Right. Now, what is the unit of E in this case? If I want to know what the unit is of our field, it is always expressed in a certain number of newtons of force E will endure divided by the amount of charge that you bring into, or that is in, that certain field. So, in other words, it is expressed in an amount of newtons per coulombs of charge, which is incredibly similar to the unit of G when you think about it. That was also a certain amount, on Earth that was 9.81 newtons per kilograms of mass. So it is incredibly similar, meaning the definition of your electric field vector E is the Coulomb force it will endure, the object will endure, per charge that you bring into that point where you're determining E, your field vector E, right? Now this has a few implications, but I'll go into that in the next video and also give you a quick extra exercise to make that point more clear. See you then.